Hi everyone, welcome back to Chem Help ASAP. In this video, we are going to be talking about the kinetic molecular theory of gases, and we will also discuss pressure, how it works, and how it's measured. Let's get started. Let's start with the kinetic molecular theory of gases. First, the gas particles are much smaller than the volume of the space they occupy. So we consider the particles themselves to have a volume of 0. So imagine you're in a large room, and then someone comes in and places a button in the corner. Has the volume of the room changed? Yes, but not by an appreciable amount. It is still okay to assume that the room has the same volume. Our second point in our kinetic molecular theory is that the individual particles of the gas are so far apart they don't interact with each other. So imagine placing two magnets at the end of a very long table. Do the magnets have attraction to each other? Well, yes, but they're so far apart that we can assume that attraction is 0. Our third point is that the molecules of the gas are constantly in motion. Now, this means that they are also colliding with the walls of whatever container they happen to be in. And those collisions is what causes pressure. So if you've ever caught a ball or maybe kicked a ball, you have felt the pressure of that collision between either your hand and the ball or your foot and the ball. That is the same kind of pressure that is going on with gases. Obviously, it's just on a much smaller level. Our last point of our kinetic molecular theory is that the temperature of the gas is directly proportional to the kinetic energy of the gas. So the more kinetic energy the particles have, the higher the temperature of the sample of gas. The kinetic molecular theory describes ideal gases, but it is good enough for our purposes to assume ideal behavior. Now that we have established gas behavior, let's talk about pressure. Now, pressure is simply the force divided by the area. So one of the best examples I have come across for understanding pressure is when you stand on the floor either flat-footed or on your tiptoes. The force you experience when you're standing is the force of gravity. That is proportional to your mass, which is not going to change. But the area covered by your feet as you move from flat-footed to tiptoes definitely decreases. So as we decrease area, pressure increases. So if you try this exercise, you will feel more pressure on your feet when you go to your tiptoes. It makes you appreciate ballerinas a little bit more, doesn't it? Pressure was first described by a student of Galileo. His name was Torricelli, and what he did was he filled a tube with mercury. Now, just as a reminder, mercury is a metal, but it is a liquid at room temperature. So he put mercury in a tube, and then he inverted it into a dish that also contained mercury. This was the first barometer, and it looked something like this. So he has a dish full of mercury and a glass tube that had mercury in it. Now what he expected was for all the mercury to empty out into the dish from the tube, but that is not what happened. Some of the mercury emptied out, but it ended up at a certain height here. Specifically, he measured it at 76 centimeters. So what's going on here? Well, you can see from the diagram, what he was measuring was the air pressure. It's pushing down on this mercury reservoir. That forces some mercury up in the tube. That is why his level of mercury did not go all the way down. Now, this diagram shows the pressure at sea level, which is 76 centimeters. But if you went up on a mountain, the pressure would be less. And if you could carry this down deep in the ocean, the pressure would be greater. Torricelli created the first barometer. Let's talk about the units for measuring pressure. So my table over here to the right gives 5 units for pressure. There are more, but these are the 5 that you're most likely to see. All of these pressures are equivalent. So 1 atmosphere is the same as 760 millimeters of mercury. This ties in with the 76 centimeters of mercury that Torricelli measured. This 760 torr is actually named after Torricelli. Now the SI unit for pressure is Pascal, which we often convert to kilopascal. Let's do some pressure conversions. Let's say we measure a gas at 635 torr. Let's convert that to atmosphere. Here's my conversion factor. I just got it from my table here. Whenever we're converting units, we want to make sure that we get good cancellation. So this is going to convert to atmosphere, and we get 0.836 atmospheres. Let's do another example. Let's say we're starting with 3.35 atmospheres, and let's convert that to kilopascal. So here's my conversion factor from my table. I write it so that my atmosphere cancels, and I get 339 kilopascal. Let's do a couple more just to keep practicing. This time, let's start with torr, and let's convert it to millimeters of mercury. I'm going to use the numbers given in my table. So here we go, again, making sure my units cancel, and you can see I get the same answer in millimeters of mercury. So some people like to keep the conversion factor like this, and others will say the conversion factor is just 1-to-1. Either way, you get the same answer. Let's do one more conversion. This time, let's start with Pascal. So let's start with 3.96 times 10 to the 5th Pascal, and let's convert this to torr. Here is my conversion factor, writing it so that my Pascal cancels, and I get 2.97 times 10 to the 3rd torr. As we are working with gases, it is going to be important that we can quickly and easily convert between units of pressure. Even though the kinetic molecular theory of gases applies mostly to ideal gases, it still helps us understand the behavior of gases in the real world. I hope you found this video helpful, and thanks so much for watching.